Hey everyone, this is going to be the first in a three-part series on maze generators in Minecraft. In this episode, I'll be going through a bunch of existing algorithms and ranking them by how good the mazes they generate are and how feasible they are to make in Minecraft. In the next episode, I'll be going over a new algorithm that I've developed that is tailor-made for Minecraft. And in episode 3, I'll be showing off that new algorithm built with redstone. So make sure to subscribe if you don't want to miss those episodes. Before we get into the individual algorithms, just some notes on how I'll be ranking them. For how good the mazes are is a mostly subjective measure based on how easy the mazes are to solve, how visually appealing they are, things like that. For how easy they are to implement in redstone, I'll be looking at options for parallelizing the build, so you can build more of the maze at once instead of one cell at a time, how long it will take to build, and how complicated each individual cell will have to be able to follow that algorithm. So without further ado, let's get into the first algorithm, the hunt and kill algorithm. The hunt and kill algorithm gets its name because of the way it scans the grid looking for places to expand. We start by choosing a random cell, and then from there we choose a random neighboring cell that isn't part of the maze, and move into that, removing the wall. We continue this process until we work ourselves into a dead end where there are no unvisited cells to visit. At this point, the scanning phase takes over. We scan from the bottom up, looking for a part of the maze that has an unvisited neighbor, and then we continue expanding from there. When we work ourselves into another dead end, we start scanning again. We repeat this process until we reach the upper right corner of the maze during scanning, at which point we know the maze has been finished. Looking at this larger map, we can see that the main drawback to the hunt and kill algorithm is that we spend a lot of time hunting and not as much actually building the maze. You'll also notice that it generates lots of very long corridors without many branches, which leads to it being not as complicated of a maze as it might appear at first. As for redstone, the main drawback to this algorithm is that each cell needs to have two modes, the scanning mode and the building mode, leading to it being more complicated than it could be. Because the hunt and kill algorithm is both middle of the ground on the quality of mazes it generates and how easy it is to implement in redstone, it's going to be our baseline right at the middle. The next algorithm we're going to look at is the Recursive Backtracker. The depth-first search or Recursive Backtracker algorithm is very similar to the hunt and kill algorithm. We start in the same way by choosing a random cell, and we start expanding the maze by traveling into random unvisited neighbors. The main difference is that when we reach a dead end, instead of scanning from the lower left of the maze, we backtrack along the path that we've already created until we have a valid route to expand out into. We repeat this process until we have backtracked to the cell we started in, at which point we know that we have finished the maze. The Recursive Backtracker is one of the most satisfying maze generators to watch. It's easy to understand what's happening. However, with this larger maze, you can see it has the same drawback as the hunt and kill algorithm, generating lots of very windy corridors with few actual branches or forks in the path, making it a more trivial maze to solve than it would appear at first glance. The mazes generated by the Recursive Backtracker are practically identical to those generated by hunt and kill, so it's going to have the same value for maze quality. However, because it only has one mode instead of the hunting and the building mode, it's a bit easier to implement in redstone, so it's going to get 1 point higher than the hunt and kill algorithm. The next algorithm we're going to look at is called Prim's algorithm. Prim's algorithm starts by choosing a random cell in the maze and adding that cell to a list of visited cells. From there, we choose a random unvisited neighbor and move into that cell, adding it to the list as well. From here, instead of continuing, we choose a random cell in the list of visited cells and move to that one. Then move into a random unvisited neighbor from there. We continue this process, and if we ever end up in a cell that has no unvisited neighbors, we remove it from the list of cells to choose from. We then continue this process until there are no cells in the list of visited cells. With this larger maze, some of the drawbacks to Prim's algorithm become clear. It becomes much slower as the maze expands. One of the workarounds to this is to have the unvisited cells checking to see whether or not they can join the maze yet. This is how Rapscallion made his Prim's algorithm maze generator in Redstone a couple of years back. The other drawback is that all of the corridors visibly point towards the center of the maze, where generation started from. Whether or not the mazes generated by Prim's algorithm are better or worse than the Backtracker is mostly a case of personal preference. There are more branching paths and more shorter corridors, but it is also sometimes really easy to find the center of the maze and solve the maze that way. Because of that, I'm going to give it the same score as these previous two, but it is much easier to implement in Redstone, so it's going to get 2 more points than the Recursive Backtracker. The next maze we're looking at is called the Growing Tree Algorithm. The Growing Tree Algorithm can be thought of as a hybrid between Prim's algorithm and the Recursive Backtracker. Like both of those, we start by choosing a random cell in the maze and adding it to a set of visited cells. Then we move into a neighboring unvisited cell and add it to the set. We repeat this for a length of 4. Then, like Prim's algorithm, we choose a random cell in the list of visited cells and create a new tunnel of length 4 starting from there. If we ever reach a dead end, we just immediately jump to choosing a random cell in the set. Like Prim's algorithm, we know we're finished when there are no more cells in the set of visited cells. With a larger maze, it's easy to see where the Growing Tree algorithm got its name. It looks like roots or branches shooting out from the maze. You can also see that it takes care of the largest drawbacks of Prim's algorithm and the Recursive Backtracker. It doesn't have nearly as many long corridors without branches, and it doesn't visibly point back to where it started generating from. The Growing Tree algorithm is the first one that has a noticeable improvement in maze quality, so it's going to get more points there. Unfortunately, it's also a lot harder to implement in Redstone. Not only do you need to do everything you need for Prim's algorithm, you need some method of tracking how long the path you're currently on is, so you know when you need to switch to finding a new starting place. So it's going to get a couple more points on maze quality, but lose a couple of points on Redstone ability. The next algorithm we're looking at is called Kruskal's algorithm. Kruskal's algorithm is unique in that it works by visiting random walls of the maze instead of random cells. We choose a random wall to visit, and if the cells on either side of that wall don't already have a path connecting them, we remove the wall. Otherwise, we keep the wall in place. Either way, the wall is removed from the set of walls. The maze is finished once every wall in the set of walls has been visited. A larger maze for Kruskal's algorithm helps show how unique it is. Instead of growing outward like most maze algorithms, the maze seems to dissolve into focus over time. At first it's just disjointed parts, and suddenly there's a completed maze. The mazes generated by Kruskal's algorithm feel a lot like the mazes generated by Prim's algorithm, but there's much lower likelihood of having a noticeable center root, so it's going to get 1 more point than Prim's on maze quality. Unfortunately, it also would be rather difficult to implement with Redstone. instead of having the individual cells doing any of the calculations, you'd have to have something outside the maze choosing random walls each time and keeping track of which walls have been visited or not. Because of that, it's also going to get a fairly low score on ability to make with redstone. The next algorithm we're looking at is called Eller's algorithm. Eller's algorithm works by scanning through the maze one row at a time. On the first pass, we can randomly choose to remove the wall between two cells if there's not already a path connecting them. On the second pass, for each set of connected cells, we choose at least one wall to the north to remove, though we may choose to remove more. We repeat this process for every row of the maze, keeping track of connected cells even if they're connected through roundabout loops down below. The only difference is on the last row of the maze, where instead of randomly choosing to remove walls between cells, we always remove the wall between cells if the cells are not already connected. When we finish this last row, the maze is complete. The larger maze just shows how weird of an algorithm Eller's algorithm is. Like Sidewinder, it can keep going on indefinitely in one direction, but it's a lot harder to track what's actually happening to make that possible. Eller's algorithm generates very nice mazes, and it can also be tuned to be biased either more horizontal or more vertical if you want a different style of maze. However, of the ones we've seen so far, it's probably the hardest to implement in redstone. It has a lot of the same issues as Kruskal's algorithm with detecting whether or not cells are already connected, with some added complications of keeping track of which cells are connected for randomly choosing which walls need to open to the north. Because of that, it's going to get the same score as Growing Tree for maze quality, but an even lower score for ability to make with redstone. The next algorithm we're looking at is called the Sidewinder algorithm. The Sidewinder algorithm starts by connecting all of the cells on the bottom row into a single long hallway. From there, we work row by row. On the first pass of each row, we break it into smaller segments. Then, on the second pass, we choose exactly one cell in each segment to point downwards into the row beneath. We repeat this process until we reach the upper right corner of the maze. A larger maze for Sidewinder doesn't really show us much, other than how easy it is to expand the maze. The maze doesn't really get any more complicated by making it larger, though. The Sidewinder algorithm doesn't generate the worst mazes, but they're not very good. They are easy to solve, they're even easier to solve in reverse, but they're also very easy to implement in redstone. The fact that each row can be generated independently makes it even faster to do it in a modular manner. So it's going to get a 2 on the maze quality, but it's going to get an 8 out of 9 on ease of implementing with redstone. The next algorithm we're going to look at is called the binary tree algorithm. The binary tree algorithm is probably the simplest maze generation algorithm there is. We visit each cell. If there's no neighbors to the south or the west, we don't do anything. If there's no neighbors to the south, but there is a neighbor to the west, we open the wall to the west. If there's a neighbor to the south, but not to the west, we open the wall south. And if we have a neighbor to the south and neighbor to the west, we randomly choose one of those walls to open. We repeat this process until we have scanned every cell in the maze. A larger binary tree maze doesn't really reveal much. It seems that it could be expanded infinitely in either direction without really adding complexity. Solving it when you can see the entire maze is also trivial. You just start in the top right corner and take the path either left or down, and you'll find the path to the exit. The binary tree algorithm does generate the worst mazes of the generators I'm demoing today, so it's only going to get 1 point on maze quality. However, it's even more suited to redstone than the Sidewinder algorithm. Each cell can operate completely independently, meaning it can generate mazes very fast. So while it's only getting 1 point on maze quality, it's getting full points on ease of making with redstone. The next algorithm we're looking at is the Recursive Division algorithm. The Recursive Division algorithm starts with no walls, forming a single large room. Then we randomly choose a place to divide that into 2 smaller rooms, leaving a single wall open connecting them. We repeat this recursively for the other 2 rooms, breaking them into smaller rooms until the room is either 1 block wide or 1 block tall. We repeat this recursively until we've visited the entire maze. The larger maze makes it even easier to see some of Recursive Division's drawbacks. It's prone to these areas with lots of long parallel corridors, and overall just isn't a visually appealing maze to look at. There's a lot of varying quality in the mazes generated by the Recursive Division algorithm. It can generate some pretty nice mazes, but a lot of the time you get just lots of very long parallel corridors. So it's going to get 3 points for maze quality. It's also not super easy to implement in redstone. While this is probably one of the easiest ways to generate a maze if you're drawing it by hand, tracking the concept of a room with redstone would be rather tricky, so it's only getting 3 points on ability to make with redstone. The next algorithm we're looking at is a variant of recursive division that I'm calling binary division. The binary division algorithm is effectively a subset of the recursive division algorithm, with the added rules that we always divide rooms down the middle, and that we alternate which direction we divide rooms in, effectively turning every square room into 4 smaller squares. Like recursive division, we recursively repeat this process until each room is either 1 block tall or 1 block wide. With the larger maze, it's easy to see the fractal nature of the binary division maze, that it's a maze made out of smaller mazes. This does make it easier to solve if you have a top-down view. One of the other benefits to this maze is that you can take the 2x2 or 4x4 or larger sections and combine them into single larger rooms without worrying about introducing loops or dead ends. This makes it ideal for planning dungeons for an RPG, even if it's not necessarily the best suited to redstone in Minecraft. Even though the binary division algorithm is in some ways simpler than recursive division, I think it actually generates better mazes. You're less likely to have lots of those long parallel corridors, you're less likely to have long stretches that cross the entire maze. But I don't think it's necessarily as good as Prim's algorithm. The maze is too predictable. If you're looking at it from the top, it's easy to just solve each level of the maze one at a time because of its fractal nature. But it is also very well suited for redstone. Because of its nature, the time it takes to generate is just the time of the largest segment. All of the smaller segments will have finished generating before that one's done. So I'm going to give it 4 points here on maze quality, just behind Prim's algorithm, but 8 points on ease in making with redstone. The next algorithm we're looking at is called Wilson's algorithm. Wilson's algorithm starts by choosing one random cell and marking it as finalized, then choosing another random cell to create a loop-erased random walk from until we hit a finalized cell. This means that each turn we choose a random neighbor to move into. If that neighbor is unvisited, we expand our tunnel into that cell. If the neighbor is already part of our tunnel, we erase everything after that and restart. We continue this until we randomly move into a cell that is marked as finalized, at which point we finalize everything that's in the path and choose another random cell to start a walk from. We continue this until every cell in the maze is marked as finalized. Wilson's algorithm has the unique property that the mazes it generates form a uniform spanning tree, which essentially means that any possible maze is equally likely as any other possible maze. However, it's one of the least satisfying maze generators to watch generate. It looks like we're making progress with the loop erased random walk, only for large chunks of that progress to just be undone. And there's no real knowing how long it's going to take to connect. Can increase the speed 2, 4, 8 times, not making progress, and then suddenly we connect, and then we start making a lot faster progress, but we still have chances we just get stuck not connecting to the maze for a while, until finally everything all comes together at once at the end. The mazes generated by Wilson's algorithm are certainly some of the best. Because it forms a uniform spanning tree, it's going to get a full 9 points on maze quality. Unfortunately, it is very poorly suited to redstone. The loop erased random walk alone is something that would take a ton of circuitry to implement. Adding to that, needing to keep track of which cells have been visited or not, and then randomly choosing a new unvisited cell each time a loop is connected to the main body of the maze. And I'm not going to say this is impossible with redstone, but this would be very, very difficult to implement. So it's only going to get 2 points on redstone, but it does get the full 9 points on maze quality. The next algorithm we're looking at is the Aldous-Broder algorithm. The Aldous-Broder algorithm is another very simple algorithm. We start by choosing a random cell in the maze. From there, we choose a random neighbor. If that neighbor is unvisited, we remove the wall between our current cell and the neighbor. Otherwise, we just move into that neighbor without doing anything new. We repeat this process until we have visited every cell in the maze. Like Wilson's algorithm, the Aldous-Broder algorithm does form a uniform spanning tree. However, you can see its main drawback here with the larger maze is just how long it takes to finish generating. We're not generating very fast. Sometimes we're just not making any progress. There's individual cells that get left behind for long periods of time. I can increase the speed 2, 4, 8, 16 times faster. You can see we're making some progress now, but we're still leaving cells behind. 32, 64, 128 times faster. Eventually, we get all of these cells in the corner, but there's really no way of knowing how long the maze is going to take to finish. Because the Aldous-Broder algorithm forms a uniform spanning tree, it's getting full marks on maze quality, but it's not going to get great marks on redstone. Even though the main redstone is really straightforward to build, it's just not a practical maze generator because of how long it takes the maze to finish. So it's going to get 5 points on the redstone, but max points on maze quality. The next algorithm we're looking at is a hybrid of the Aldous-Broder and Wilson algorithms. The Aldous-Broder-Wilson Hybrid algorithm tries to combine the strength of those two algorithms. It starts with Aldous-Broder's algorithm, which is better at growing at the start, finalizing cells until we've visited about a third of them. Then we switch to Wilson's algorithm, performing loop-erased random walks to connect the rest of the cells to the finalized chunk of cells, until every cell is finalized. While the hybrid algorithm does a decent job of mitigating the drawbacks of the Aldous-Broder and Wilson algorithms, it still has some of the same issues. The first part still gets caught up with large chunks of time, not really making any progress, leaving empty cells behind. And once we switch over to Wilson's algorithm, we still have the same problem of sometimes just not making any progress and undoing our loop. So it's a decent hybrid. It's faster than either of the algorithms on their own, but it's still not perfect. As you may have guessed, this one is going to get maximum points for maze quality, but this one is going to get minimum points for ability to make with redstone. It has all the worst parts of Wilson's algorithm, plus it needs some way to switch between Aldous-Broder and Wilson, do everything Aldous-Broder does, and have some way of detecting when we're at that 1/3 complete threshold to be able to switch which algorithm we're using. Because of that, yeah, it's going to get minimum points for redstone quality, but maximum points for maze quality. The last algorithm we're going to be looking at is called origin shift. The origin shift algorithm is an algorithm for modifying mazes. We start with this very simple maze, where each cell is either pointing to the south, with the wall to the south open, or pointing to the west, with the wall to the west open, except for the origin, which is in the southwest corner. Each turn, we move the origin into a neighboring cell. The old origin now points into that cell, and that new cell doesn't point anywhere. We repeat this process for an indeterminate amount of time. Each step along the way, the maze is still a fully connected maze, so we can just run it until we're satisfied with the result, or we can even run it while someone is trying to solve it, because it's a finalized maze every step along the way. Compared to Aldous-Broder and Wilson, origin shift is much more satisfying to watch generate. We don't really get stuck in times where we feel like nothing is happening. There's always something changing in the maze, even if we're not necessarily expanding any farther. There is a drawback that we could just have these long parallel corridors for huge chunks of time without really knowing how long it's going to take to get rid of them, and we don't really have a way of knowing when we're done or should be done generating the maze. That said, every step along the way, it is a completed maze, so you don't actually have to wait for the maze to be finished before somebody can start running it. Overall, it's a fun maze, and you should check out Captain Luma's videos linked below, going over how he developed the algorithm and implemented it in Minecraft. Because the maze changes over time, it's kind of tricky to score origin shift. At the start, after giving it just a little bit of time to run, it's not going to have the best quality mazes, but give it the time it takes to run Prim's algorithm or so, you'll have a decent quality maze. So it could go right here at the start, or once it's run for a while, it could go here in the last column with the highest quality mazes, and slightly more suited to redstone than Aldous-Broder, just because you don't need to worry about detecting when you're finished, so it could go here. Just to have a single score for origin shift, I'm going to give it an 8 out of 9 on maze quality, and a 7 out of 9 on ease to build with redstone. And with that, here's my final ranking of these 14 algorithms. It's fairly subjective, but I think it does a good job of showing an overview of the pros and cons of different algorithms. If you disagree with my ranking, if you think I was too nice or too harsh on an algorithm, feel free to leave a comment below or join the Discord and chat at me there. If you want to watch as I create a new algorithm tailor-made for Minecraft, make sure to subscribe so you can catch those next couple of episodes. And with all that, thank you for watching, and I hope you have a nice day. See you all in the future.